Welcome to the Explainer. So, today we're taking a really fascinating journey through the invisible architecture that literally powers our entire modern world. We rely on this digital ecosystem every single day. But how often do we actually stop to think about how the whole shebang works? Well, in this Explainer, we're going to trace that exact path, right from the absolute basic infrastructure of our digital world all the way up to the incredibly complex protocols we use to lock down and secure our most sensitive data. It's going to be a great ride. So, let's dive in. Okay, just to map out where we're headed, here's a quick look at our agenda. First up, the internet versus the web. Second, locating and retrieving websites. Number 3, the role of cookies. 4 is digital currencies and blockchain. 5, modern cybersecurity threats. And finally, number 6, defending our digital data. All right, let's jump right into section 1, the internet versus the web. So I actually want to kick things off by challenging a really common misconception here. You see, we all use the terms internet and World Wide Web interchangeably, basically all the time, right? But technically speaking, they are absolutely not the exact same thing. The internet is actually the physical infrastructure. It's this massive worldwide collection of interconnected networks and devices, and they communicate making use of transmission control protocols, or TCP, and IP protocols. Honestly, it helps to just think of the internet as the physical roads and highways. The World Wide Web, on the other hand, well, that's what's actually traveling on those roads. It's the huge collection of multimedia web pages that you access via browsers using HTTP or HTTPS protocols. So simply put, you use the internet to send an email, but you use the World Wide Web to browse a website. Make sense? Okay, moving on to section 2, locating and retrieving websites. So if the web is this massive collection of pages just sitting out there on a global physical network, you might be wondering, how exactly do our devices navigate this gigantic infrastructure to actually find the specific information we want? Well, web browsers don't actually understand words. They absolutely need an IP address to retrieve pages. And this is exactly where a domain name server, or a DNS, steps in. Think of the DNS as a massive digital phone book. You give it a name, and it instantly looks up the exact number. Let's actually walk through that exact 5-step process because it's pretty wild. Step 1, you just type a URL into your browser, like you always do. Step 2, your browser shoots off a request to the first DNS server asking for the IP address. Now, if it doesn't know it, step 3 kicks in. It asks a second DNS server, which searches, finds the URL, and securely maps it to a specific IP address, something that looks like 107.162.140.19. Then, step 4. That numerical IP address is sent straight back to your computer. And finally, step 5. Your computer uses that IP address to set up a direct communication line with the website server that allows the HTML code to be downloaded right to your screen. And the craziest part? This entire 5-step dance happens in a fraction of a second. Right, on to section 3, the role of cookies. Now that we're successfully connected to a website, how exactly does that website remember who we are or what we're even doing? Well, that's where cookies come in. Cookies are just these tiny little files stored on your computer by a web server, and they act kind of like a little lookup table. But keep in mind, not all cookies are created equal. Basically, we have session cookies and persistent cookies. Session cookies are totally temporary. They're the ones that remember your virtual shopping basket while you browse around an online store, but the second you close your browser, poof, they're deleted. They don't collect personal info. Persistent cookies, however, are a different story. They stay on your hard drive until a set expiry date. They essentially serve as a longer-term memory for the web, remembering your passwords and, yes, tracking your browsing habits across different sites to serve you targeted ads. Which brings us to section 4, digital currencies and blockchain. So we've got the network infrastructure, the web pages, and the tracking sorted. But how does all of this underlying architecture support modern financial technology? Well, before we can even talk about cryptocurrency, we really have to define the technology that actually makes it possible, and that is blockchain. You see, traditional digital currency relies heavily on a centralized bank to manage things. But a blockchain, it's a completely decentralized database. When a transaction happens on a blockchain, every single networked computer in the entire system gets a copy of it. And that's a real game changer because it removes the need for state control or central banks, and it tackles huge security issues by making all transactions totally public and traceable. So, when a new cryptocurrency transaction occurs, a brand new block is created. These blocks are then chained together sequentially, one after the other. Fun fact, the very first block in this entire chain is actually called the Genesis block. But wait, you might be thinking, how do we ensure someone doesn't just sneak in and change the data inside one of these blocks?
This is the absolutely crucial point. It's all about how these blocks are mathematically locked together. Every single block contains its own transaction data, a unique hash value generated by an algorithm, and the hash value of the previous block. So imagine a hacker illegally accesses one block and tries to change the transaction data. The moment they do that, that block's hash value instantly changes. And because it no longer matches the previous hash value that's permanently recorded in the next block down the line, the link is broken. Just like that. The entire network immediately knows the data has been tampered with. It's just a brilliantly elegant security solution.
All right, let's look at the darker side of things in Section 5, modern cybersecurity threats. Because let's face it, wherever there's valuable data and money, there are inevitably people trying to steal it. Let's pivot our narrative a bit and look at the actual digital battlefield. I want you to really consider this provocative question for a second. How do cybercriminals manipulate human emotion? We always picture hackers in dark hoodies, furiously typing green code to break through some massive firewall. But the reality? The easiest way into a system is often straight through the user. This is what we call social engineering. It's terrifyingly effective, because complex technical hacking isn't even required. The victim willingly drops their guard. Cybercriminals are absolute masters at exploiting 3 specific human emotions. First up is curiosity. A criminal might literally just leave a malware-infected memory stick lying on the ground in a company parking lot. Human curiosity practically guarantees that someone is going to pick it up and plug it into their computer just to see what's on it. Bam, they're in. Second is empathy and trust. This is where you get those highly convincing fake emails pretending to be from well-known companies or charities, tricking you into clicking a malicious link. And finally, fear. Have you ever been browsing and suddenly seen a screaming pop-up warning that your computer is infected, and you absolutely must download this specific antivirus software right now? That's scareware. They are weaponizing your panic to make you willingly download malware. Now, contrast that sort of human manipulation with a technical threat like farming. Farming requires absolutely no action from the user whatsoever. What happens is malicious code is silently installed on your computer or a web server, very often through something called DNS cache poisoning. Remember our giant digital phone book we talked about earlier? Well, farming basically poisons that phone book. So you sit down, type in your actual bank's real web address, but the poisoned cache instantly redirects your browser to a perfectly designed, completely fake website just to steal your login info. And the scary part is, you wouldn't even know it happened. And of course, then we have the much broader category of malware. We've got viruses, which actually need a host program and require you to actively click something to execute them. Worms, however, are way more dangerous. They're standalone programs, which means they can spread like wildfire across an entire network, jumping from computer to computer without any user action at all. Then we also see Trojan horses, which cleverly disguise themselves as legitimate software. There's spyware, silently logging your every keystroke, adware, driving you crazy by flooding your screen with pop-ups, and ransomware, which literally takes your data hostage, locking it behind an encryption key until you pay up a hefty fee.
Wow, okay, it sounds pretty terrifying, right? But don't panic just yet. Let's head into our final section, Section 6, Defending Our Digital Data.
Let's focus on the actual defense mechanisms and security protocols that keep this whole digital ecosystem safe. The absolute first line of defense, and one you interact with every single day, is SSL, or Secure Sockets Layer. Whenever you see that little HTTPS or the padlock icon up in your browser's address bar, a really neat 4-step process is happening in the background. Step 1, your browser requests a secure connection. Step 2, the web server sends over a copy of its SSL digital certificate. Step 3, your browser authenticates that certificate to ensure the site is exactly who it claims to be. And Step 4, once it's fully authenticated, a secure 2-way encrypted data transfer begins, meaning even if someone managed to intercept that data mid-flight, it would be totally unreadable gibberish to them. Beyond encryption, we're also seeing a massive, massive shift toward biometric authentication, basically using who you are to physically prove your identity. And there are pros and cons here. Fingerprint scans, for example, are super easy and require very little storage space, but they can easily fail if your skin is cut or damaged. Retina scans, they offer incredibly high accuracy with absolutely no known way to replicate them, but they are super expensive to set up, and honestly, they feel a bit intrusive. Face recognition is wonderfully convenient, sure, but changes in room lighting or just natural aging can really throw it off. And while voice recognition is incredibly fast and easy, well, catching a simple cold could completely lock you out of your own device. But here's the real secret. Ultimately, true security doesn't ever rely on just a single wall. It relies entirely on layered defenses. This means combining a bunch of different things. Think about two-step verification, where you need a password and a one-time passcode sent straight to your phone, or firewalls that sit right between you and the wild internet to carefully filter incoming and outgoing traffic. We use proxy servers to hide your IP address. We set strict access levels so users only ever see the specific data they actually need to see. And honestly, one of the absolutely most effective defenses is also the simplest: automatic updates. Just letting your device run its updates overnight quietly patches the exact software vulnerabilities that hackers and worms are actively looking to exploit.
Well, we've covered a whole lot of ground today, right? From the basic routing of IP addresses to the cryptographic hashes of blockchain, all the way down to the messy psychology behind cyber threats. So I want to leave you with this final kind of provocative thought. Knowing just how interconnected and vulnerable our data truly is, and knowing that cybercriminals so often target human emotion way more than they target computer code, what do you think is the single weakest link in your own personal digital defense? Food for thought, right? Thank you so much for joining in on this explainer, and I'll catch you in the next one.